Hello. This is a talk on Chapter 4, Part 2, on directed graphs. In this talk, we will focus on longest paths in directed acyclic graphs. Consider the following directed acyclic graph. It has vertices and it has edges. And we're focusing here on vertex V10. And we're interested in longest paths that end in V10. So I've marked here 3 paths that end in V10. The first path is the orange path. It consists of a single edge, E7, and therefore its length is 1. The green path consists of E0, E3, E6, E10, E12, and has 5 edges, therefore its length is 5. And the blue path goes over here and also consists of 5 edges, therefore its length is 5. You may ask, is there a path that ends in V10 whose length is greater than 5? And you can verify that that is not possible. Therefore, these 2 paths, the green path and the blue path, are longest paths that end in V10. Given a path gamma, we denote the length of gamma by the absolute value of gamma. Namely, the absolute value of gamma is the number of edges along gamma. Consider a path gamma that ends in a vertex V. We say that this path gamma is a longest path ending in V if for every path gamma prime that ends in V, the length of gamma prime is not longer than the length of gamma. As we've seen in the previous example, we may have more than one longest path ending in a vertex. Hence, we say a longest path rather than the longest path. Consider a path gamma in the directed graph. We say that the path gamma is a longest path in gamma if for every path gamma prime, the length of gamma prime is less than or equal to the length of gamma. Now you may ask, does every directed graph have a longest path? Consider the following example. I have a directed graph here that consists of 4 vertices, A, B, C, D, and the edges from A to B, from B to C, from C to D, from D to A. Now, as you can see, this graph consists of a simple cycle. So what I could do is I could take a path that starts in A, goes to B, goes to C, goes to D, goes to A, goes to B, goes to C, goes to D, and continues in that fashion as many times as I want. So I can go around this cycle as many times as I want. Therefore, this directed graph does not have a longest cycle. Does not have a longest path. That means that for every n, there exists a path gamma such that the length of the path gamma is greater than n. Okay? Good. Now, if we are focusing on DAGs, these are directed acyclic graphs, then we claim that indeed, in a DAG, there exists a longest path that ends in V for every V. In addition, there exists a longest path in G, in the whole DAG. And the proof is very simple. It's based on the fact that we have already proved that the length of every path in a DAG is at most the number of vertices minus 1. Therefore, since the length of every path is bounded by this number, we know that there must exist a longest path. Alternatively, Every path in the directed acyclic graph is simple. We've also shown that. Hence, the number of paths is finite, and among a finite set of paths, we can take a path of longest length, and that will be a longest path in the graph. Provided, of course, that it is acyclic, that it doesn't contain any cycles. Okay. Our goal is to compute for every vertex v in a directed acyclic graph a longest path that ends in v. So instead of computing the path, let's consider a simpler task of computing the length of a longest path. We denote the length of a longest path that ends in a vertex v by d of v. So, we want to design an algorithm called longest path that is given as input a directed acyclic graph G with a set of vertices V and a set of edges E. Our goal is to compute a delay function D defined over the set of vertices, and this function D assigns to every vertex V the length of the longest path that ends in V, and we denote this length by d of V. Why are we interested in this question? The reason we're interested in this question is we will model combinational circuits by directed acyclic graphs, and then, for example, if we assume that every gate in the circuit has a delay of 1 unit time, then the delay of the output of a gate V would equal d of V. So this would give us a tool for analyzing the timing of a circuit. Let's try to compute the delays of vertices in a directed acyclic graph. Okay. We start with the source. What is the longest path that ends in a source? Well, the in-degree of a source is 0, and therefore we have no edge which enters V0, and therefore the length of the longest path that ends in V0 is 0. So we write d of V0 is 0. Good. Now we look at V1. V1 has in-degree 1. Every path that ends in V1 has to come from V0. A longest path that ends in V0 has length 0. So after adding this edge E1, a longest path that ends in V1 would have length 1. The same argument works also for V2, because there's a single edge that enters V2, again from V0. So we can write here 1. What about V3? The in-degree of V3 is 1. Every path that enters V3 does that through V1. Every path that enters through V1 has length at most 1, and there is a path of length 1 that enters V1. Therefore, our longest path that reaches V3 has length 2. The same argument holds for V4, because there's a single edge which enters V4. It enters V4 through V2, and we already computed the delay of 1 for V2, so we know that the delay of V4 is 1 plus 1, namely 2. We continue now to look at V5. V5 has 2 edges that enter it. The first edge comes from V3, and the second edge comes from V4. Both of these vertices are labeled by 2. Their delays are 2. Therefore, the delay of V5 is 2 plus 1 equals 3. Indeed, we have 2 paths of length 3 which end in V5. The first path goes like this, and the second path goes like this. As you can see, these paths have delays along them of 0, 1, 2, 3. Very good. The same argument tells us that the delay of V6 is 3. The delay of V7, having a single edge that enters it from V6, is 4. The delay of V8, having a single edge that enters it from V5, is also 4. Now let's look at V10. V10 has two edges that enter it. The first one from V7, whose delay is 4, and the second one from V0, whose delay is 0. So what V10 says is that I could have paths reaching me either from V0 or from V7. And the longest path that enters me would actually come from V7. Its length up to V7 would be 4, and now there's an extra edge, E12, in order to reach me, so therefore my delay is 5. And the same argument holds for V9, 5. So we've computed the delay function of the vertices in this specific example. How would a general algorithm for computing longest path lengths in a DAG work? So assume that the graph V, E is a directed acyclic graph. Our goal is to compute the delay function d of V for every vertex in the graph. How does the algorithm proceed? The first step we do is we apply the topological sorting algorithm to the vertices to obtain an ordering of the vertices in the set V. This ordering is denoted by V0, V1 up to Vn minus 1. Okay, so V0 is the first vertex in the topological ordering, and Vn minus 1 is the last vertex in the topological ordering. And of course, n denotes the size of the set V. Having sorted the vertices of V in topological order, what we do is we scan the vertices one by one from the first vertex until the last vertex. This is what this for loop does. J is an index that goes from 0 to n minus 1. Now, when we look at Vj, we have two options. Either Vj is a source or it's not a source. Well, if it's a source, then we know that the longest path that ends in a source is of length 0 because there are no edges which enter the source. And therefore the delay of Vj is 0. That's an easy case. What do we do if Vj is not a source? If Vj is not a source, we look at all the Vi's such that there is an edge from Vi to Vj. Now, by the topological sorting property, we know that I has to be strictly less than j. For every such vertex V from which there is an edge to Vj, we look at its delay function d of Vi, and we take the maximum among all these vertices. To this delay, we add a 1. This is exactly what we did in the previous example. When we looked, for example, at V9, and it saw two vertices from which there are edges to V9, their labels were 3 and 4. We took the maximum of 3 and 4, which is 4. We added a 1 to it in order to get 5. Okay. People often ask me whether you could design this algorithm to run faster, because in fact there is here some scanning of the vertices in this stage of the topological sorting, and here we're scanning the vertices again. Could we do everything in a single pass? The answer is one could do that, but then it would be harder to prove the correctness of the algorithm. So we use topological sorting as a black box with all the properties that come along with it in order to prove that the assignment of delays to vertices in this for loop indeed computes the delay function of the vertices. Let's see how we do that. Before we do that, I want to show you an example of how the algorithm is executed. Okay. So the first thing we do, we sort the vertices in topological ordering. So we have the vertices A, B, C, D, and we apply topological sorting to them to get the order V0, V1, V2, V3. Good. Having sorted the vertices in topological order, we now scan them. We start with V0. We see that V0 is a source, so therefore we assign d of v0 to be 0. We proceed to v1. v1 has only one incoming edge from v0, whose delay is 0. So we take 0, we add 1 to it, and therefore d of v1 is 1. v2. Now we scan v2. v2 has a single edge entering it from v1. The delay of v1 is 1. We add 1 to it, and therefore the delay of v2 is 2. Finally, we look at v3. v3 has two edges which enter it, one from v2 and one from v0. So d of v3, by the definition of the algorithm, is 1 plus the maximum of d of v0 and d of v2. Now, d of v0 is 0, and d of v2 is 2. So we conclude that d of v3 should equal 3. Okay, this explains an execution of the algorithm on a small graph. Good. Now what we want to do is we want to prove the correctness of the algorithm. So we have two quantities. The first quantity is the output of the algorithm. The algorithm assigns to every vertex v some d of v, and this d of v should equal delta of v, where delta of v is the length of the longest path that actually ends in v. And our goal is, of course, to prove that d of v always equals delta of v. Here, this is the theorem that deals with the correctness of the algorithm. So in order to prove that the algorithm longest path is correct, we need to show that for every j, d of vj indeed equals delta of vj. The proof of the theorem proceeds by complete induction on j. It's a rather complicated proof. We will go over the details in a second. Let's start with the basis, the induction basis. The induction basis for v0 is very simple, because in fact, for any node which is a source, the algorithm assigns d of vj to be 0, and we know that delta of vj is also 0. So in fact, for sources, which also includes the induction basis for v0, the proof is very easy. Okay, recall, the proof is complete induction. So the induction hypothesis is, for every I less than or equal to j, d of vi equals d of vi, delta of vi. Now in the induction step, we want to prove the equality for vj plus 1. So we want to prove that d of vj plus 1 equals delta of vj plus 1. So I want to emphasize, our hypothesis is that for I less than or equal to j, d of vi equals delta of vi. In the step, we want to prove that d of vj plus 1 equals delta of v of j plus 1. The proof consists of two parts. In order to prove equality, we prove that delta of vj plus 1 is greater than or equal to d of vj plus 1, and that delta of vj plus 1 is less than or equal to d of vj plus 1. These two inequalities combined give us the desired equality. Now let's try to understand what these two inequalities mean. The first inequality means that the maximum length of a path that ends in vj plus 1 is not less than what the algorithm computes. Namely, there exists a path that ends in vj plus 1 whose length is at least d of vj plus 1. The second part that we want to prove is that the longest path that ends in vj plus 1 has length which is not greater than d of vj plus 1. Namely, we want to prove that every path, gamma, that ends in vj plus 1 has length which is less than or equal to d of vj plus 1. Okay, so our proof will be divided into two parts. Let's start with the first part. Okay. In the first part, we need to show there exists a path gamma that ends in Vj plus 1, whose length is greater than or equal to d of Vj plus 1. The first case, Vj plus 1 is a source. This is easy, as I pointed out in the induction basis. So let's assume now that Vj plus 1 is not a source. And for simplicity, let's assume that its in-degree is in fact 3. It could be any number, but the proof would also work with any number. But to make the proof clear, let's assume that the in-degree is 3. So this is Vj plus 1. There are 3 edges that enter Vj plus 1. And the nodes from which these edges emanate are denoted by Vi1, Vi2, Vi3. And recall that the algorithm assigns Vj plus 1 a delay of 1 plus the maximum of the delays of Vi1, Vi2, Vi3. So this is the value of d of Vj plus 1. This is what the algorithm does. Good. Now, among these 3 vertices, Vi1, Vi2, Vi3, let's assume that the algorithm gave Vi2 a delay which is not less than the delay of Vi1 and the delay of Vi3. This means that this maximum actually equals the delay of Vi2. And therefore, the delay of Vj plus 1 simply equals 1 plus the delay of Vi2. Good. Now, topological sorting tells us that because there is an edge from Vi2 to Vj plus 1, the index I2 has to be strictly less than j plus 1. The induction hypothesis, when applied to I2, tells us that there exists a path, gamma prime, ending in Vi2, whose length is no less than the delay of Vi2. Now we know that we can take gamma prime and extend it by an edge from Vi2 to Vj plus 1. Here, look at this drawing. This is my path ending in Vi2, we call it gamma prime, and to this path we add the edge from Vi2 to V of j plus 1. Now, what is the length of this path? Here it is, gamma prime extended by Vi2, comma, Vj plus 1. Notice that I use this small circle to denote concatenation of paths, or an extension of the path by an edge. This is a path that ends in Vj plus 1, as you can see here in the drawing. Its length is the length of gamma prime plus 1 edge. Now, by double star, this is the induction hypothesis, in fact, the length of gamma prime is not less than the delay of Vi2. And by our assumption on Vi2 having the maximum delay among Vi1, Vi2, and Vi3, we know that this value equals d of Vj plus 1. Therefore, there exists a path whose length is greater than or equal to the delay of Vj plus 1, and that completes the proof. Let's prove now the second part. We want to prove that delta is less than or equal to d. Okay, what do we need to prove? We need to prove that the maximum length of a path ending in Vj plus 1 is not greater than the delay of Vj plus 1. Namely, we need to prove that for every path gamma that ends in Vj plus 1, the length of gamma is not greater than the delay of Vj plus 1. We consider 2 cases. The first case is where the length of gamma is 0. Well, if the length of gamma is 0, then clearly 0 is less than or equal to the delay of Vj plus 1, because the delay is never negative. The function d of Vj plus 1 is never negative. The algorithm never assigns negative values. So this clearly holds. The second case, assume that the length of gamma is strictly positive. Let Vi denote the predecessor of Vj plus 1 along the path gamma. So we have this last edge in gamma, and we denote the vertex from which this last edge in gamma emanates from by Vi. So gamma is in fact the concatenation of a path gamma prime ending in Vi with an edge from Vi to Vj plus 1. Okay? Now, topological sorting tells us that I is strictly less than j plus 1 because we have an edge from Vi to Vj plus 1. The induction hypothesis, when applied to Vi, tells us that the length of gamma prime is not greater than the delay of Vi. Now we put things together. The length of gamma equals the length of gamma prime plus 1 because gamma prime plus this edge is in fact gamma. Now, the induction hypothesis applied to gamma prime tells us that it is less than or equal to d of Vi. And d of Vi plus 1 is less than or equal to d of Vj plus 1. Why is this? This is because the delay of Vj plus 1 was taken to be 1 plus the maximum delay of a vertex from which there exists an edge to Vj plus 1. And when we took this maximum, we also included in this maximum the delay of Vi. So we know that the delay of Vj plus 1 is greater than or equal to 1 plus the delay of Vi, and this completes the proof. I want to conclude with the following question. Suppose that we're not interested in the length of a longest path that ends in V. Instead, we want to actually find such a path. We want to find a longest path. Our algorithm just tells us what's the length of a longest path ending in V, but it doesn't tell us what the path, such a path actually is. Can you modify the algorithm so that it will not only tell us what is the length of a longest path ending in V, but it would also tell us such a path? Thank you.